Good day, everyone. I am Silo Jane Dr. Domingo from 12 STEM, and in this video, I will discuss and teach you about relativistic Doppler effect. First, let's define what is Doppler effect. When an ambulance passes by, you hear its tone change pitch. This phenomenon is manifested by waves, including sound and light, and is called the Doppler effect or Doppler shift. When the ambulance is still at rest and the siren is on, a stationary observer from a given distance will hear the exact same frequency and tone from the ambulance. If, however, the ambulance starts to move, as shown in the illustration, the observer on the right will hear a higher tone from the ambulance. In other words, Doppler effect is the frequency shift resulting from a wave source's motion relative to an observer. To understand relativistic Doppler effect, apply the Doppler effect to light waves. The formula for relativistic Doppler effect is F equals square root C plus U over C minus U multiplied by F sub 0, where F equals frequency from the observer's frame, C is the speed of light in free space, U is the speed of the source with respect to the observer, and F sub 0 is the frequency measured in the rest frame of the source. Meanwhile, wavelength is the distance between two crests. For wavelength shift, the formula is this. How is frequency affected by the motion of a source? When the source heads toward an observer, the perceived frequency f is larger than the generated frequency f sub 0. This difference is called the Doppler frequency shift, or change in frequency equals generated frequency. When u over c is less than 1, the change in frequency over frequency is small and nearby equal to u over c, or change in frequency over f equals u over c. When the source heads away from the observer, the sign for u is reversed, such as this formula becomes f equals c minus u over c plus u multiplied by f sub 0. A galaxy is moving away from Earth with a speed of 0.900 c and is emitting radio waves that have a wavelength equal to 0.600 m. Determine the wavelength that will be measured by an observer on Earth. First, let's identify the given values: the speed and the wavelength. And it also says here that we are looking for the wavelength, so the formula we will use is the formula for the wavelength shift. Using the formula, we will substitute the given values and we will have this. The answer will be 2.62 meters. The wavelength emitted by the radio waves from the reference frame of an observer on Earth is equal to 2.62 meters. For the next problem, a spacecraft travels at a speed 70% that of light in free space and beams a signal of frequency 1 times 10 raised to 7 Hz. If this light moved across the direction as the spacecraft's motion, solve for its Doppler shift if the spacecraft is heading towards Earth. The given is a speed of 70% and a signal of frequency which is 1 times 10 raised to 7 Hz. It also says here that we are solving for its Doppler shift if the spacecraft is heading towards Earth. So the formula we will use is f equals square root of c plus u over c minus u multiplied by f sub 0, or the formula for Doppler shift. Using that formula, we will substitute the given values and we will have f equals square root of c plus 0.70c over c minus 0.70 multiplied to 1 times 10 raised to 7 Hz, and we will have f equals 2.38 times 10 raised to 7 Hz. The frequency resulting from the Doppler shift is 2.38 times 10 raised to 7 Hz. Since the spacecraft is moving towards a stationary frame, the perceived frequency has increased. For the next problem, a very fast-moving jet plane has a frequency of 6.45 times 10 raised to 14 Hz. From the frame of reference of the jet, the light from the jet has a frequency equal to 5.50 times 10 raised to 13 Hz. Determine the speed of the jet plane from the frame of an observer on Earth. Let's identify the given values, and we have frequency, which is 6.45 times 10 raised to 14 Hz, and the light from the jet has a frequency equal to 5.50 times 10 raised to 13 Hz. And it also says at the end of the problem that we should determine the speed of the jet plane from the frame of an observer on Earth, which means we will derive u from the formula of Doppler shift, and we will have the formula u equals c multiplied to f over f sub 0 squared minus 1 over f over x sub 0 squared plus 1. Using this formula, we will substitute the given values, and we will have the answer u equals 2.96 times 10 raised to 8 meter per second. The speed of the jet relative to the observer is 2.96 times 10 raised to 8 meter per second. That would be all for our lesson in this video, which is the relativistic Doppler effect. I hope you were able to learn from my discussion. Thank you and bye!